Here are solutions to homework set number 3 for ECE 376. On this homework set, we're looking at binary inputs, binary outputs, and timing, along with LEDs. So the first problem is a binary output. I've got a temperature sensor. I want to measure temperature. Specifically, I want to come up with an input that outputs 0 volts when the temperature is less than 10 degrees Celsius, 5 volts when it's more. So one way to do that is to use a thermistor. This is a temperature-sensitive resistor. The temperature versus resistance relationship is exponential, looking like this. As temperature goes up, R goes down. Convert resistance to voltage with the volts divider. This 1K is kind of arbitrary. Ideally, I want this to be 2.5 volts, or these two to match that you're switching, but it doesn't have to be exact. That goes to a comparator, and this voltage determines where you're switching. So to start out, I want to find out what's the resistance at 10 degrees Celsius. Plug in 10 and you get 2002 ohms. Pick your favorite voltage divider. I chose a 1K resistor, so at 10 degrees Celsius, this is 3.33 volts. That's where I'm switching. In terms of the plus or minus input, think about the extremes. When the temperature is really, really hot, this should be 5 volts. When it's really, really hot, like 1,000 degrees, this is almost 0 ohms, 0 volts. I want V plus to be more than V minus when it goes high. So this goes to the minus input. The plus input is the temperature or voltage corresponding to 10 degrees Celsius. So there's your circuit, and the VI characteristic looks like this. At 0 volts, when it's really, really hot, I get 5 volts out. When it's cold, I get 0 volts out, and I switch at 10 degrees Celsius. And this is just a straight line up and down. That's a comparator. Problem 2 says now add hysteresis. What I want in terms of temperature is something like this. I turn off at 10 degrees Celsius. I turn on at 15 degrees Celsius. So again, the procedure is first measure temperature, use a thermistor to convert temperature to resistance, use a voltage divider to convert resistance to voltage. So same as before. I chose a 1K resistor, again kind of arbitrary. Then the off voltage is 3.3, on voltage is 3.0. And I like drawing this in terms of voltage rather than temperature. The circuit cares about voltage, so the on voltage is 3.059. That's where it turns on. The off voltage is 3.33. When the on voltage is less than the off voltage, connect to the minus input. Otherwise, connect to the plus. The on voltage is where you switch, so that's your 3.05 volts. And the slope is the gain. The output changes by 5 volts as the input changes by 0.3 volts for a ratio of 18 to 1. So pick this to be 18 to 1. And I pick this to be large because actually this is 190K in parallel with R. That changes R, changes the voltages, changes the circuit. Make this large, and it's not too bad. So like this affects the resistance by like 1%. So my numbers are actually about 1% off. If you want to be dead on, what I could do is add a buffer. A buffer is just an op-amp circuit going like this. The input impedance to an op-amp is about 4 gigaohms, basically no loading, and then you'd be more accurate. But it adds another op-amp. So that's problem number 2. Problem 3 is kind of a tricky one. I want to do this instead. I want to turn on at 10 degrees Celsius and turn off at 15 degrees Celsius. Come up with a circuit that does that. Now there's multiple ways of doing this. One approach is go back to problem number 1. I can do temperature greater than 10, temperature greater than 15, just change the offset voltage. Feed that to a microprocessor. Then in software, I want to do A bar B. It's not bigger than 15, but it is bigger than 10. That's one way to do it. Second way is, if you get kind of tricky, I can start using diodes as an AND function. The first one is going to be temperature greater than 10. The second one is temperature less than 15, and I want to do A and B. One way to do that are diodes. This is a min function. A min is basically the same thing as and. The output is high only if A is 5 volts and B is 5 volts. If either one is 0 volts, the diodes turn on and it takes Y, ties it to ground. And the 1K resistor is just a pull-up resistor. When both these are turned off, I set the voltage to 5 volts. So that's something you're going to cover in electronics. That's the min function using diodes. Also DTL logic. But a couple ways of doing it. This works. You can use software. I kind of like saying anything you can do in software, you can do in hardware, vice versa. So either solution is fine. And there's others. Problem 4. Come up with a circuit so your PIC can drive an RGB LED at full power, 20 milliamps. So in that case, the LEDs have a 1.9, 3.2 volt drop. I know that when this is on, this is 5 volts. But when the current to be 20 milliamps, the resistance is just the voltage drop, 5 minus 1.9 over 20 milliamps, 150 ohms, 5 minus 3.2 over 20 milliamps, 90 ohms. So this circuit lets a PIC turn on and off the LEDs independently. If I want to use a bigger LED, like a 5-watt LED, I've got a problem. A PIC can't drive 250 milliamps. It can't drive, say, 6.5 volts. So I need a buffer. That's the transistor. That's this circuit right here. The PIC controls the base voltage, turns it on and off. When the input is 0 volts, there's no current flow. This simply means diode. No current flow means off. When it's 5 volts, I want this to turn on and saturate. When it saturates, this is roughly 0.2 volts, ballpark. The LED has a fixed voltage drop, say 6.5 volts. Pick your favorite power supply. I chose 12 volts. The remaining voltage goes across R. So to set R, take the remaining voltage at 250 milliamps. R is 21.2 ohms. To set the base current, if this is 250 milliamps, the current gain is 300. That's your HFE or beta. Depends upon which textbook you're using. That divided by 300 is the minimum base current. The base current has to be at least 0.8 milliamps. The biggest it can be is 25 milliamps, because that's all the PIC can do. So pick a number bigger than 0.8, less than 25. It's really kind of arbitrary. I chose 4.3. Once you pick the current, find the resistance RB. If this is 5 volts, this is 0.7. Again, this is a diode. Voltage drop across the silicon diode is 0.7 volts. 4.3 volts at 4.3 milliamps is 1K. And this can actually vary quite a bit. As long as you get between 0.8 and 25 milliamps, RB is fine. Problem 6 looks at timing. Come up with a way to play note E4. That's 329.63 Hertz. Now to do that, what I'm going to do, I'm just going to toggle a pin, and the time delay between toggles is the number of clocks. That should be 10 million divided by 2 times Hertz. The 2 because there's 2 toggles per cycle. 10 million clocks per second. I want to wait 15,168 clocks. So one way to do that is this loop right here. This is 10 clocks. Called A times B times. The red section is 4 clocks, or 4 instructions plus 1, 5 clocks times A. The black section is 1, 2, 3, 4 clocks. Plus I have to call for the main routine, plus another go to, gives 9. So the total number of clocks for this routine is 10 times A times B, that's this inner loop, plus 5 times A, that's the red section code, plus 9. That should be 15,168. Find A and B to get you close. Subject to the constraint that all numbers have to be between 1 and 255. These are 8-bit registers. The biggest number is 255. And they have to be integers. So playing around a little bit, one combination that came close is 7 and 216. That gives you 15,164. A little bit off. So there's 7 and 216. The acid test is to try it. So here I've got the Piano Tuner app running. The PIC is driving an H bridge that drives the speaker. Here's the frequency. 329.4. That was noisy. So that worked. The last problem is build a stoplight. So what I want is this. So here's my counter. It goes through 14. So there's 7, 8, 9, 10, 11, 12, 13, 14. Goes back to 0. These are the lights. The east-west goes green, yellow, then red, then back to green. When east-west is red, north-south is green, yellow, red, and so on. So here's one side, currently green and red, yellow, red, red, green. How do you do that? Well, first off, you have to assign the pins. So I'm going to find port C to be the east-west light, north-south to be the port D, with the LEDs corresponding to green, yellow, and red, one for each direction. Here's the duration. When I write to the ports, the color is the bit pattern. So to turn on the green light, I want to turn on these two. That's hex 03. To turn on the yellow light, that would be hex 0C. And to turn on the red light, that'd be hex 30. So when I write these numbers to the port, that sets the color to green, yellow, or red. In terms of the flowchart, a couple ways of doing this. What I did is kind of reuse the code from homework set number 2. I'm going to count mod 14. On 0, I go to green, 5, yellow, 7, red, red, green, and then 12, red, yellow. Wait 1 second, then repeat. Now to get that code to work, I'm going to do a thing called top-down programming. What I'm going to first do is get the wait routine to work, then get the counter to work, then get the lights to work. So here's my main routine right here. I'm just going to initialize the ports, count, drive the lights, wait 1 second, repeat. Let's start out, I just want to get the counter to work. So I'm going to count, and to see if the count's working, I'm going to count on port C once a second. So here I compile, just down so you can see it, build, not sure what that was, hit reset, download the code. What I should see on port C is it counts once per second. And actually when I did this first time, it just locked up. If there's a mistake in your routine, your count routine, like I don't have the counters being initialized right, I can get an infinite loop. Infinite loops show up as you hit reset and it just stares at you. It's locked up somewhere. Fix all the infinite loops, get it to be 1 second, and I should get it to count once per second. Okay, so at this point, I now have the wait routine working. Once I get the wait routine working, let's get the mod 14 counter to work. So this is counting mod 14. I'm going to increment seconds. If it's 14, go back to 0. Then move seconds to port A. So once I'm happy here, let's turn on this routine. Compile. Download. And now here's port A counting. There's 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. 14 go back to 0. Okay, so now it's counting once per second, counting mod 14. Once that works, I'll then get the lights. I'm going to check on 0, I go green, 5, yellow, 7, red. I check for 0, 5, 7, and 12. Once you get the first two parts working, compile, download. Check the last part. There's 5, it went to yellow, then red on 7, 12, 13, 14, goes back to 0. And there you have a stoplight. Thing to note is when you're writing your code, if you try to write it, get it to work all at once, if you're like me, you'll get really frustrated. Go in baby steps. Get the code to work step by step. Can I get it to count once per second? Once it does that, can I get it to count mod 14? Once I get that, can I get it to turn on the green light at 0, yellow at 5, red at 7, and so on. Kind of go step by step. And that's called top-down programming. What it typically looks like is something like this. I've got different subroutines. Get them to work one at a time. Start with the one that you display your data, because it helps to have something to see. And then add features. But that's homework set number 3 for 376.